Okay, so our next unit is going to be primarily concerned with rates and rate laws. Now, rate is just something over time. We're most familiar with rates when we're talking about driving in cars, where we're going miles per hour. That's a rate. Or, if we're, paying somebody per hour, like if we pay a tutor, that's also a rate because it is an amount of money, say $20 per hour that you're paying somebody. So that's a rate. Now, when we talk about rates in chemical equations, it's a little bit different. And usually we're talking about molarity per second. That's the most common rate. And, in other iterations of the problem, you might get, molarity per hour or something like that if it's a slower reaction. Um, but what you're looking at is you're looking at the production of a concentration over a certain amount of time. Now, I've brought a kind of simple problem today, and this is a theoretical reaction. Obviously, we don't have A's, B's, and C's, but just reactant A plus 2 of reactant B yields product C. Now, AP, and I put this up so I could read this exactly. AP says that the rates of change of reactant and product concentrations are determined by the stoichiometry in the balanced chemical equation. So if we think about this as a balanced chemical equation, what's going to happen here is as this reaction is happening, A is going to seem to be disappearing, okay? So your reactant's rate of disappearance, because when you're doing a chemical reaction, what it seems like is the reactants are disappearing, but they're not disappearing. They're just being transformed into product, okay? But what they're saying here is since it takes 2 of the B and 1 of the A, the B is going to look like it's disappearing twice as fast. So the rate of disappearance of B is going to be twice that of the rate of disappearance of A. So if you're losing 1 mole per second of A as the reaction shifts to products, you're going to be losing 2 moles per second of B because you need 2B, so it's going to look like it's happening twice as fast. Whereas the rate of appearance of C should be exactly the same as the rate of appearance of A, but only 1/2 of that of B, because B is disappearing twice as fast as A. You see you got a 1 here, coefficient, a 1 here. So the A and C rates are going to be the same, and B is going to disappear twice as fast as A, and C is only going to appear half as fast as the B disappears because B is double, okay? But I can show you this a whole heck of a lot easier. So on the problem that I have here, it says that B is decreasing at 0.5 moles. 0.50 moles per liter per second. Okay. And so and then it asks how fast is A decreasing? Well, we can kind of just figure that out, but I want to show you some things here. First off, moles to liters -1, that's just another way of writing molarity. Okay, so 0.50 molarity per second. And when you're talking about rates, you got to get used to this idea of molarity per second because that's what most of our rates are going to be in. So moles over liters, that -1 for the liters, that's all that means is it's moles over liters, that's molarity. And I just usually put it as a big M, molarity over seconds. So if B is going at 0.5 molarity per second, how fast is A going? I mean, the obvious answer here is that A is going at 0.25 moles liters seconds, like that. But another way we could look at it is I take the 0.5 molar per second of B, and I want to switch that into A, 1 mole of A, 2 moles of B, boom, boom, like that, because I have 1A for every 2B, and so the answer would be 0.25 molarity per second. So that's the first part. It's not that bad.